Hello everyone, myself Vinay Mishra, the faculty of Mechanical Engineering Department of Malika Institute of Management and Technology affiliated with AKTU. Today we are going to have a discussion for the subject Thermodynamics of BTech third semester from AKTU syllabus. In our previous lecture, we have talked about some thermodynamics aspects like first law of thermodynamics, second law of thermodynamics, entropy, the concept of entropy, how the entropy is related to our life, how the entropy changes for the universe, and about availability, about available energy, about unavailable energy we have talked about. Continue with that lecture. Today we are going to have a same discussion for the concept of entropy in the second law of efficiency in the context of thermodynamics. So, as we have learned that what is available energy and what is unavailable energy. We have seen this definition, the maximum amount of useful work that can be obtained from the system such that the system comes to a dead state. That means, the maximum amount of useful work that can be extracted from the given amount of heat, the maximum amount of useful work, I am using the word useful, the maximum amount of useful work that can be extracted from the given amount of heat input, that is said to be available energy when the system reduces at its dead state condition. About this we have talked about. Now, dead condition state, the dead state meaning the kind of equilibrium is there, the kind of equilibrium in between the system and surrounding is there. That means, mechanical equilibrium, thermal equilibrium and chemical equilibrium. So, we can say the kind of thermodynamic equilibrium is there in between the system and surrounding. In that condition, the maximum amount of work extracted from the system itself, that is known as available energy. Now, if the maximum amount of work is there, if the maximum amount of work is extracted from the system, then basically we have the two parts of the heat given. That means, if the given amount of heat is being given to the system, that must be divided into two parts. The first one is the useful work and the second one is unuseful, or we can say which is rejected in nature. Now, work output and heat rejected. That means, this Q1 is being divided into two parts. The first one is the work output, the second one is the heat rejected. If this one is maximum, if work output is maximum, we can say that the rest amount of heat, the rest amount of energy is being minimum, because it is being divided into two parts. The first one is this, the second one is this one. So, if it is maximum, this must be minimum in nature. This maximum is said to be available part of energy, and this the part of energy is said to be unavailable part. So, if we talk about the nature, if we talk about the universe, if we talk about earth, then in our current scenario, the problem is associated with the availability of energy. We say that there is an energy crisis, but one of the most important thing that I need to tell you that there is nothing like energy crisis exist in our earth, because the earth consists of infinite form of energy, we can say. We are using the word infinite in the sense we are having energy resources in a large number. We are having energy sources in the form of wind energy, in the form of solar energy, in the form of geothermal energy, in the form of petroleum energy. There is nothing like energy crisis exist for earth, because the earth is having sufficient amount of energy content into it, but the problem is associated with the available part of energy, because still the large amount of energy is there, but in large amount of energy we are only concerned for the utilization part of energy that can be utilized, that can be useful for us. That means that useful energy we are having basically crisis of that kind of useful energy. So, we can say we will never use the word like there is energy crisis, no, definitely not. We are having the energy crisis in terms of available energy, because we are having large amount of energy, but the kind of energy we can extract, the kind of useful energy, basically we are having the problem with that. Okay. So, we can say that there is a available part of energy crisis exists in earth. For example, the main source of our energy is solar energy, we can say, but the part of solar energy we can utilize, that is only 7 to 8% or more or less equal to that, one. So, only we can use the small part of energy, the small part of solar energy, the rest of the energy is being rejected, or we can say is of no useful. So, we will never use the word, we will never say that the energy crisis are there, energy crisis is there, definitely not. We are not having energy crisis, we are having a sufficient amount of energy, we are having sufficient amount of energy resources with us, but the problem is associated with the utilization, the problem is associated with the useful extraction of work from that available part of from that energy. So, definitely we can say that the kind of energy crisis, if we talk about the energy crisis, that we are in that condition, we are considering the available part of energy, not unavailable part of energy. So, okay. So, this one is the maximum work output, that is said to be available part of energy, and of course, if it is maximum, this must be minimum, this must not be equal to 0, because as per Kelvin Planck statement, this must not be equal to 0. Of course, there should be some rejection. Now, this rejection is minimum, and this amount of minimum rejection is known as unavailable part of energy. Okay. Minimum energy that is rejected from the system as per second law is known as unavailable part of energy. Now, about second law of efficiency. See, as per definition, the second law of efficiency is defined as the ratio of the actual thermal efficiency to the maximum possible reversible thermal efficiency under the same condition for heat engine we are talking about. Okay. So, basically the second law of efficiency deals with the ratio of actual thermal efficiency to the maximum possible thermal efficiency of the system for the same condition we are talking about the heat engine. See, if we talk about efficiency, the first law of efficiency and the second law of efficiency, then we see that the second law of efficiency deals with the quality, deals with the quality output, deals with the quality performance of the system itself, and the first law of efficiency, which we have already discussed, that deals with the quantity of performance what we are getting from the system itself. In case of second law of efficiency, definitely the term second law of efficiency says that how much the performance is there for that particular system if we are talking about its quality, not quantity. Okay. In the same, we can say that it is basically the ratio of actual performance to the maximum performance. Okay. If in particular field, suppose take the example of myself, I can perform 70% with the best of my performance. I can perform in my life 70% with the best of my performance. In that condition, if I will perform 60%, that means and in second case, if I perform only 20%, in that case the 60% the performance is my quality as compared to my performance at 20% with respect to my maximum performance that was 70%. I am going to explain you with some example of this second law of efficiency. This is basically your engine, this is basically your heat engine. The T1 is the temperature of source, the temperature of reservoir. I am using the word reservoir. Just see, in most of the time I will be using the word reservoir for this one, this one, this one, this one. That means reservoir is something in which the temperature of the body remain constant even if the kind of heat rejection is there. In reality, if a certain amount of heat is being rejected from the system, in that condition the temperature goes down, but reservoir we are assuming that it is a reservoir. If we are using the word like reservoir, that means the temperature of this body remain constant even if the rejection of heat is there. Even if the rejection of heat is there, Q1 is still the temperature remain constant. So, we can say it is a reservoir. In the second one, if this is a sink which is at temperature T2, this is also same working as a reservoir, because we assuming that its temperature remain constant even if the amount of heat is being continuously added to the system itself. Here you can see the amount of heat added, that is equal to Q2 continuously to the system itself, and still its temperature remain constant. In that condition, we can say that this one is working, this one is used as a reservoir. Moreover, if we take the example of surrounding, and some amount of heat is being added to the surrounding, then what will happen? The surrounding is infinite, air is infinite on earth, air is infinite in space. So, we can say the surrounding is working as a reservoir. That means, with giving continuous amount of heat, there is no effect on the temperature of surrounding, or if we take certain amount of heat from the atmosphere, we can say the temperature of the atmosphere remain constant. Now, T1 is the reservoir at temperature 800 Kelvin, and T2 is the reservoir at a temperature 200 Kelvin. Q1 is the amount of heat added to the system, that must be equal to 600 kilojoule. The amount of work output what we are getting outside from the engine itself, that is equal to 300 kilojoule. The amount of heat rejected, this is equal to kilojoule, 300 kilojoule. This one is equal to this one plus this one, the algebraic sum, okay, because from the heat balance equation we can say that Q1 is equal to W plus Q2, 600 is equal to 300 plus 300, simply 600. In the second question, in the second part of this engine, here you can see that this one is the reservoir at temperature 600 Kelvin, this one is the reservoir at temperature 300 Kelvin, this one kilojoule, basically these are kilojoule. Q1 is the amount of heat added to the system, that must be equal to 600 kilojoule. We are taking some say example in order to understand the second law of efficiency of the system itself. Heat engine, work output is 300 kilojoule, the heat rejected, that is equal to 300 kilojoule. Simply 600, 300 plus 300. Okay. Now, say this one is engine A, this one is engine B. Now, if we calculate the thermal efficiency of this engine, if we simply calculate the thermal efficiency of this engine, that must be equal to ratio of output what we are getting from the system itself and the input what we used to give to the system itself, that is equal to Q1. That means, for this the thermal efficiency equal to 300 divided by 600, 50%. Thermal efficiency of A, this must be equal to output what we are getting from the system itself, and the if we divide it by the amount of heat given to the system itself, that is equal to Q1, then we will have the value of thermal efficiency or actual efficiency, the same is equal to the actual efficiency of the system itself. So, we can say the thermal efficiency as well as the actual efficiency of this engine A is equal to 50%. Okay, very good. If we talk about this, if we talk about engine B, we will calculate thermal efficiency of B, that must be equal to simply 300 divided by 600. The output what we are getting from the system itself and amount of input, the ratio of output to the input, the amount of input what we are giving to the system itself, that must be equal to the amount of heat input, that is equal to Q1 and 600 kilojoule in case of this particular heat engine B. It will come like 50%. Okay. Now, the most important point, this engine is working between 800 and 200 Kelvin. We are giving the certain amount of heat, that is equal to 600 kilojoule, and the amount of work what we are getting from the system itself, that is equal to 300 kilojoule, and the amount of heat rejected, that must be equal to 300 kilojoule. In this case, the working temperature limit are different. This is working under 600 Kelvin and 300 Kelvin. The amount of work what we are getting from the system itself, that is equal to 300 kilojoule. The amount of heat input to the system, that is equal to 600 kilojoule. The amount of heat rejected to the system, to the surrounding, that is equal to 300 kilojoule. Now, we see in terms of quality, sorry, in terms of quantity, if we will say in terms of quantity what we are getting exactly from these two engines, then we will simply say this one is performing in such a way that we are getting the work done equal to this one, simply in terms of quantity. The same for engine B, we are getting the same amount of work done, 300 kilojoule over here, the same amount of work done we are getting 300 kilojoule over here. And when we talk about its efficiency, thermal efficiency, actual efficiency, then we see it is performing, its performance is somewhere equal to 50%. Now, if we talk about the efficiency of this one, we see the efficiency is around 50%, the same efficiency. That means, for this we are having maximum we are having the efficiency of 50%. For this engine also we are having the efficiency of 50%. In this case we are having output in terms of work output, that is equal to 300 kilojoule. In this one we are having work output in terms of work output, that is equal to 300 kilojoule. If we concerned for quantity, then definitely this engine performance are same. The performance of A and B are same, but if we concerned for the quality, if we concern for the quality, then we see the performance of these two engines are somewhere different. See, if we talk about its maximum efficiency, this one is actual efficiency, under this condition only this one is working and we are getting the amount of work done over here. But if we talk about the maximum efficiency of this possibility when the engine is working between these two limit 200 kelvins in and 800 Kelvin, and that condition we have to find out its maximum possible efficiency of this engine when it is working under 200 and 800 Kelvin. In that condition simply what we have to calculate simply Carnot cycle efficiency, because it is a benchmark that gives you the idea that till how much efficiency the device can perform, or we can say what is the best performance of the device or heat engine working under certain limit of temperature, that is being calculated from Carnot cycle efficiency. So, if we calculate the Carnot efficiency of this one, then this is equal to 1 minus 200 divided by 800. 200 1 minus T2 upon T1. This equation we have already proved in our previous lecture. We have already discussed in detail in our previous lectures. So, we see that its Carnot cycle efficiency or its maximum possibility of generating efficiency is equal to its Carnot efficiency, or can be considered at its Carnot cycle efficiency, that must be equal to 1 minus T2 upon T1. T2 is the lower temperature, T1 is the high temperature. Simply what we are getting over here 75% for A, C for Carnot cycle efficiency and A for this designation. So, the maximum possible efficiency for this engine A, that must be equal to 75%. That means for this given condition of T1 and T2 without considering this much, for the given condition of this T1 and T2, this engine can perform the best in such a way that its efficiency becomes 75%. That means, if it is performing very well, if during this when the temperature difference are like this, in that condition this can generate efficiency up to 75%. Now, here if we talk about B and we find out the efficiency of this engine in terms of Carnot cycle efficiency, or if we find out its maximum efficiency, then this must be equal to 1 minus this upon this. %. Now we see, now the main point, we are having the same amount of output over here, we are having the same amount of actual efficiency over here, we are having same amount of actual efficiency as well as work output 300 thermal efficiency, actual efficiency 50, but if we talk about the maximum efficiency, if we talk about its maximum performance, then we see that it will come around 75%, and if we talk about the performance of B, maximum performance of B up to which it can perform very well, which must be equal to its Carnot cycle efficiency, as we have discussed in earlier lecture. In that condition we can say that its Carnot cycle efficiency must be equal to 1 minus T2 upon T1, 1 minus T2 upon T1 for the given temperature limits, that is coming around 50%. That means now the question, now the concept comes. See, for the particular instant, this one is producing efficiency of 50%, instead of the fact that it can produce 75%. It produces, it performs in a way that its efficiency is equal to only this much, somewhere less than this one. It can produce 75%, but this instant it produces only 50%. Now this one, for any instant its efficiency is 50%, but it can perform 50%. That means if we are talking about this 50% as an actual efficiency, in that condition we can say that a heat engine B is performing its maximum. The performance of heat engine B is maximum, which is equal to 50%, which is equal to 50%. That means under, if we talk about any particular instant, this particular instant, in that condition we can say this engine performs very well as compared to this engine, okay, because its relative efficiency is less. If we talk about its relative efficiency, it might have performed very well, but it performed only 50%. It can perform 75%, but for this instant its performance is only 50%. But in this case this can perform 50%, and for this instant it is performing its 50%. That means its performance is basically the maximum. The performance of this heat engine B is maximum for any given instant. So, we can say the quality of this engine B is somewhere better as compared to this one. So, we can simply calculate its second law efficiency, that must be equal to 50 divided by 50, what we are getting 1. That means 100%. If we talk about the quality of the engine, this is performing 100%, 50 divided by 50. Now, if we find out the second law of efficiency for this particular engine, we find that the second law of efficiency is equal to actual efficiency divided by maximum efficiency. Actual efficiency is 50%, maximum efficiency is 75%. It will come less than 100%. So, we can say simply the performance of this engine A is less as compared to the performance of engine B. In this way, we have seen that what is second law of efficiency and how it is useful for the quality concern of efficiency. Okay. So, in coming lectures I will be discussing, we will discuss some more topics related to that. Okay. Thanks a lot.